So today we are going to talk about some examples of dimensional formula. So some examples of dimensional formula. We are going to talk about some pretty unique ones. So I'm going to use three colors today. So big day, okay? It's a big day. So you don't need to understand the formulas, why they come about, because we will discuss them in future videos in their respective chapters. But you need to know how to get the dimension of the following things. So I'm gonna teach you, but I'm not gonna teach you very accurately how to find the dimension of them. I'm just gonna give you what they are. So if you need them for any purpose, you can find them pretty easily. So first one we are gonna talk about is mass. So mass, it is represented by m, and it has a dimension of m1 l0 t0. You can also write m only, and you cannot write, and you don't need to write t0 or l0. So I could have written it as m, but I will follow the MLT format. That's why in the previous video I said we do not write Kelvin, K and other things, because they are all raised to the power of 0, and you don't need to write them if they are raised to the power of 0. You only need to write them if they are raised to the power of 1 or more than 1. So next one which we are going to talk about is length. So these are the very simple ones. We are getting down to the basics. So the length, it will be 0 and L1 T0. I hope this is pretty clear right now. And the third one is time. Third one is time. It is M0 L0 T1. So a trick when doing dimension analysis or finding the dimensional formula of anything, you can find it pretty easily by using the units rather than doing it by a formula method. So when I talk about units, here we know the unit of length is meter. That's why it's L to the power 1. But when doing this trick, I will also tell you more about this trick when we get to further formulas and for the dimensional formulas. But most people, when I teach this trick, get confused in the fact that meter is for length, not for mass. Here there is m, but this is m is for mass, not meter. So let's look at some examples. So these are the basic ones, so I will do more of them in the next page. So we are at number 4. So let's start, which is area. So area, its dimension is m0 l square t0, because the formula of area is L into B. I think you know this. It is a pretty famous and clear formula. It is not the most. It is not the only formula of area, by the way. It's the most simplest that I know of. So L into B. So this might be still confusing for some people. So think about the units. Length will be in meter. Breadth will also be in meter, because breadth is also a length. Length is also a length. So meter square is the unit. So since meter square is the unit, the dimension must be L squared. So I told you, don't think of Lm square as this m. It is meter squared. So it will be much more easier if you said kilogram per meter squared or meter square, meter cube, rather than saying kg meter per second square. So even if you say it like that, try to say meter, because it will make it much more easier when finding the dimensional formula. The next one is volume, and volume is also pretty simple. It is m0 l cube t0, because the formula that is most common is L into B into H. Of course, there is a formula of L cube, but that will be very much. I mean, that is not such a common formula that everyone knows it. That's why I'm using L into B into H, which is the very basic formula of volume. Another one, the sixth one, now we're going to talk about velocity. I think you might know of velocity. It is m0 l1 t minus 1, because the most common formula of velocity is displacement over time. So displacement with a d, I'm represented representing E by D. I'm not representing it the arrow because we don't care about that right now. So next one we're going to talk about is acceleration. The dimensional formula of acceleration is m0 l1 t minus 2, and the most common formula that you will find of it is velocity upon time. So we already know the dimension of velocity, so if we divide time again we will get t minus 2, from t minus 1 to t minus 2, because we have divided by time once more. The another one is 8, which is force. The dimension of force is, we have also derived this right now, so which is mlt minus 2. Let me write one over here, one over here. The most common formula that you might find of force is mass times acceleration, which comes from Newton's second law of motion. So this one is very important because it will be used for a lot of other derivations, because many formulas have force in them. So let's talk about the next one, which is 9, which is pressure. So the dimension of pressure is m l minus 1 t minus 2. I will not write m to the power 1 right now unless I find it necessary or I do it by accident. So the most common formula of pressure is tangential force per area. So we know the dimension of force, so dividing by area we also know it of the dimension of area, which was L square. We would get m L minus 1 t minus 2. So the next one, the 10th one we are going to talk about is work. So work, the dimension of work is m L square t minus 2, because the most common formula of work that you will find is F into D, which is force times distance. So this is work is also a very important dimension that it will be better for you to remember. If this was an ideal world where you can do calculations forever, then I would not recommend to remember any of them, because physics is not about remembering, it's about understanding. But since most of you are watching this for exams or are for learning purposes, for quick calculations, it will be much more beneficial to know the dimension of force and work, because they are very useful and they help us to do find of many others, because the dimension of work is the same as of energy, same as kinetic energy, potential energy, etc, etc, which we will talk about later and why that is. So now let's talk about power. The dimension of power is m L square t minus 3. And the most common formula that you will find of it is work per time, since power is the rate of doing work. So when we are talking about rate, we do something by respect to time, so dividing it by time. So another one, the 12th one, which we are going to talk about, is linear momentum. Linear momentum, its symbol is P and it's an axial vector, so we will talk about them when we get to the chapter relating to them, because I don't know the exact chapter, so I don't want to mislead you, but we will talk about them in some other video. So the most common formula you'll find of it is m into v. So another one is 13. It is torque, and its symbol is tau. It might sometimes also be written as couple, and here you can write this as ml2 t minus 2, and the most common formula that you will find of it is F into R. F into R is not the exact formula, it's a special case of the formula, but we are using the most simplest case of the formula. Okay, to get the dimension quickly. Also, I think I said linear momentum was an axial vector. I may be wrong. I think I'm wrong. Let me check real quick. Okay, I just checked it. Yes, I was wrong. Linear momentum is a polar vector because it's occurring linearly. Polar vector, we will talk about them in vector chapter. And axial vector includes rotation, and since linear momentum is happening in a plane which is linear, so it will not have any rotational component. That's why it's a polar vector. If you wrote somewhere, or if you thought that linear momentum was an axial vector, it's wrong. Okay, it's a polar vector. So linear momentum is a polar vector. I saw momentum and I thought of angular momentum. Mistake. Another one, 14, we are going to talk about is impulse. So the dimension of impulse is mlt minus 1, and the most common formula that you will find of it is F into t, so force into time. The next one, which is 15, we are going to talk about is charge. Its symbol is Q. I'm writing the symbol of a few of them because they are something they are not commonly heard of, or you might not have heard of them, so I'm just introducing them to you. So M0, M0, L0, T1, A1. Oh my god, why is there a A? So why is there a A? Why is there a A? So you might be like that. So it's because the formula of charge, the most common formula of charge that you will find is I times T. I meaning current and T meaning time. Since current is the rate of flow of charge, so it's Q by T. So we can write Q as I into T. And if you think about it, I meaning current, which means current is a fundamental quantity, so it cannot be described by any other unit or quantity, which means that you can't describe um, current by mass, length, or time, which is a big problem. That's why we use A. Do you remember the fundamental unit of current? It was ampere, right? And the symbol of ampere was A. That's why we write A to the power 1. We did not write any other of them, any A to the power 1 over here, because in other cases it was A to the power 0. So we don't need to write dimension if its power is raised to 0. Okay, let's move on. Next, 16, we are going to talk about electric potential. Electric potential, and its symbol is represented by V. So this kind of V is a very funky kind of V. It's not your typical V. So there are two bars, as you can see here, two bars over the V. So don't forget to make that. And also here in tau, it's not a normal kind of T. It's a T with a bend shape. So it's like an opposite J, writing the capital J as oppositely. So electric potential, the formula of electric potential is M1 T square, M1 L square T minus 3 A minus 1. Why? Because its formula is work done per charge, work done divided by charge. Actually, I want you to actually think about this. I just told you to know the dimensional formula of work done, which was m L square by T minus 2, and the dimension of charge that we just found out was T1 A1. So dividing m L square T minus 2 by T1 A1, we get m L square T minus 3 A minus 1. So think about it. I think you got it. So now 17, we are going to talk about electric field intensity. So what is electric field intensity? Doesn't matter right now, but its symbol is E, and its dimension is m1 l1 t minus 3 a minus 1, and its formula is F upon Q, force upon charge. So now let's next one, 18. We are going to talk about potential gradient. A quick note that you might need to know, whenever we talk about gradient, it's always a vector. You don't need to know what a vector is. Just remember that it is a vector, because we will talk about vectors in the next chapter. I think the next chapter is about vectors. It might be or it might not be, I'm not quite sure. But when we talk about vectors, I will give you a very detailed explanation about vectors. Here, dV meaning change in potential, electric potential, and dr meaning change in distance. You can also write x. I'm writing r over here. Okay, you can also write x. It does not matter, anything or something that represents the distance. Now next one is frequency. The frequency, its symbol is f, and its dimension is pretty simple. It's m0 l0 t minus 1, because the most common formula of frequency is 1 over time period. When we write capital T, it means time period. So it is a time for something to occur, whereas small t represents time taken or the time. It can be any moment of time. It does not need to be significant. But capital T, time period, is kind of significant. Okay? So the next one, which we are going to talk about, 20, is angle. So which angle is this, you might be thinking. We are talking about the solid angle. Here we are talking we are talking about plane angle, but for solid angle also the dimension would be same. Just to let you know, it would be the same. So the dimension of plane angle or angle in general is m0 t0 l0 t0. We generally write mlt because they are the most common units that occur. That's why we prefer to write them all, but you don't need to write them. So because it is defined as arc length by radius. So arc length is a length, radius is also a length. So meter by meter, which is nothing, 1. Let's say 1. So that's why it has no dimension. So, but do you remember that we told that it has a unit? Plane angle has a unit, which is radian. So this is quite a good realization to realize that the units, just having a unit does not mean it has a dimension. But having a dimension always means that it has a unit, because dimension occurs due to some units, the fundamental units, if they are present. Okay, the next one we are going to talk about, 21, is angular velocity. Angular velocity, it is represented by omega. It's not W, okay? It definitely looks like W. I'm not gonna lie, but it's not W. And its dimension is m0 l0 t minus 1. So please don't get confused, because here is velocity. The term angular changes its dimension, because we are not dealing with lengths, where we will be dealing with angles, or that's why in angular velocity we don't have the same dimension as of linear velocity or the normal velocity. So in most cases the velocity will always be lt minus 1, unless for angular velocity, because in other cases it would be always length upon time. But here it is angle upon time. We will talk more about them in another chapter that we will get. So all of these units we will talk about in a chapter that will come up. Surely it will come up. I don't know when, but it should come up. The next one we are going to talk about is angular acceleration. So angular acceleration is represented by alpha. So it's like when the teacher does it's wrong and it does like this, it's basically the same symbol, very similar symbol. Okay, and its and its dimensional formula is m0 l0 t minus 2, because its formula is omega by t, so it's angular velocity upon time. So it here you can also realize that acceleration and angular acceleration do not have the same dimension. So this is also a very good insight to have. Another one that we are going to talk about is moment of inertia. Moment of inertia, which is represented by the capital I, and its dimension is ml square t0, because its most common formula is mr square. Another one that we are going to talk about is velocity gradient. So 24, it is velocity gradient. So if you remember, I told you that gradient means it is a vector. Since velocity is already a vector, it does not matter right now, but even if the term initially was a scalar, when taking the gradient it becomes a vector due to the distance, so dr or dx parameter. So we know the dimension of velocity, we know the dimension of dr, so we can find the dimensional formula of velocity gradient pretty easily. So basically, if you know the formula, you can find the dimension. That's what I'm trying to tell you. So what I would like you to do is to make yourself more easier, to make it easier for you to find the dimension of various units or various things. I would recommend you to see the formula, then derive the dimension, because I'm not telling you to remember the formulas, because when the time comes you will remember them by yourself. But right now I'm just making sure that you know how to find the dimensional formulas of anything. If you know the formula, I want you to be able to find the dimensional formula if you know the formula. Okay? Sounds very confusing, but you get me. You get what I'm saying. Okay. Now let's talk about coefficient of viscosity. Dimensional formula of coefficient of viscosity. It is represented by the symbol eta. So it looks like an N, but the right side is elongated and it's curved. Okay. Dimension is m l minus 1 t minus 1, and here the most simplest formula is also kind of complex. So the most simplest formula is actually f divided by dv by dr, so that's velocity gradient, times a, which is area. So that's the formula. So yeah, pretty complex formula, but it comes from Newton's formula that you will learn in, I don't know which chapter, but you will learn. I will teach you that. But right now, let's move to another one. Should I write here or here? Since it will like be block here. Let's write it over here. 25 or 26. Let me check here. 24, 25. Yep, got my math wrong. So this is 25 and this is 26. So in 26 we are going to talk about gravitational constant. Its symbol is capital G. So let's talk about its dimension. It's m minus 1 l cube t minus 2, and the most common formula that you will find of it is f into r square, where r is the distance, and mm, where mm are the masses. So the formula might look complex right now, but when you learn the topic it will be pretty easy to understand what it means. 27, we are going to talk about capacitance, and its symbol is capital C, and here let's write m minus 1 l minus 2 t power 4 a square. So it's quite complex, but the formula is actually quite easy. It's just q by v. Q meaning charge and v meaning potential. I paused the video because I had to sneeze, so let's continue. um, 28, it is specific heat capacity. Its symbol is S, small s, and its dimensional formula is m0 L square T minus 2 K minus 1. As E represented current, here K represents temperature from Kelvin. I hope you understand that. So, since you got these, I think you will understand if we have quantity of matter, luminous intensity, it will be CD to the power something, mole to the power something, respectively. So, the most common formula that you will find of it is actually Q by M del theta, where theta is the temperature. I don't know if it's called theta or theta, but I will be calling it theta. I think it's theta, but I can't say it pretty well, so I'm going to say theta. So don't mind my pronunciation, since English is not my native language. I'm trying my best to speaking English to improve my English and make this video available for everyone. So with that, it's done. We are done for today. So in the next video we are going to talk about principle of homogeneity, which is quite an interesting topic.